In our last video on related rates, we're going to look at shadow problems and one trigonometric problem. And in our first example, we have a boy who is 5 feet tall walking away from the base of a street light at a rate of 3 feet per second. If the street light is 25 feet high, at what rate is the boy's shadow changing? So let's come up with a bit of a diagram here. So first of all, we have our ground. Here's our street light. Okay, and then we have our boy who is walking. Okay, and the light is shining from the top of the pole. Okay, and the shadow is being created obviously on the ground here. Okay, and we know that the boy is 5 feet tall, and we know that the pole is 25 feet high. Okay, and we know that he's walking away from the light post. So we're going to call the distance between the boy and the light post x, and this is going to be s, which represents the shadow. Okay, so the rate change of x, or the rate that he's walking away from the light pole, is 3 feet per second. So we're basically going to use the concept of similar triangles to set up an equation here. So we know that if I take the base of this right triangle, so I have one right triangle here and I have my big right triangle. So if I take my base S and divide it by the height of the boy is 5, that's going to be equal to the base of the big right triangle, which would be x plus s all over 25. Now if I was to cross multiply, I would get 25s, and if I distribute the 5, I would get 5x plus 5s. And now if I collect the s's, I subtract 5 s's over, and I'm going to get 20s is equal to 5x. And if I divide both sides by 20, I'm going to get s equals 1 over 4x. Now I can take the derivative of both sides with respect to t. So I'm going to get ds dt is 1/4 times dx dt. And now all I need to do is plug in my value for dx dt, which was given to me as 3 feet per second. So therefore, the rate change of the shadow is going to be 3/4 feet per second. So that would be the rate change of the shadow, and that would be the answer to part A. Okay. Now in part B, they want us to find the speed of the shadow. Okay. So the speed of the shadow is really going to equal the rate change of the boy plus the rate change of the shadow. So that's going to equal 3 feet per second with the rate change of the boy plus 3/4 feet per second with the rate change of the shadow. So the speed of the shadow would be 3 3/4 feet per second. Okay, in our next example, we have a man, spotlight on the ground, and that shines as a man is walking towards a wall that's 10 meters away. So now my light path is going this way, and you can see I have already indicated S on the wall, because that's going to be the height of the shadow. And as the man gets closer to the wall, the shadow is going to get smaller and smaller. Okay, and it says, a spotlight on the ground shines on a wall 10 meters away. A man 2 meters tall, so he's 2 meters, walks from the spotlight to the wall at a speed of 1.2 meters per second. Okay, so that means that I have the distance x is the distance between the man and the light. So he's walking away towards the wall. So dx dt is going to be 1.2 meters per second. Okay. And the question is asking how fast is the shadow on the wall decreasing when he is 3 meters from the wall. Okay, so if he's 3 meters from the wall, x is going to be 7. And this distance right here is going to be 3 and we know that the whole distance between the light and the wall is 10. So now we have to set up another ratio. So we're going to set up the ratio by going 2 over x, because that's the distance between the light and the man, is going to be equal to the shadow s, all divided by 10. Again, if I cross multiply, I'm going to get sx is equal to 20. And if I divide both sides by x, I'm going to get s is equal to 20 over x. So therefore, I'm going to rewrite that in a derivative-friendly form. So s is going to be 20x to the minus 1. So now I can take the derivative with respect to time. So this is going to equal negative 20 over x squared times dx dt, which is going to be negative 20 over, well, at the instant he is 7 feet from the light, and the rate change is 1.2. And if you work this out, it works out to be a negative 0.499 meters per second. I believe I'll just double check that. Yes, that negative 0.489 meters per second is going to be the rate change of the shadow. And the negative just indicates that the shadow is getting smaller as the man gets closer to the wall. Okay, our last example is our trig example. And we have a camera on the ground 200 meters away from a hot air balloon and records the balloon rising into the sky at a constant rate of 10 meters per second. How fast is the camera's angle of elevation changing when the balloon is 150 meters in the air? Okay, so the balloon is rising, and they've indicated that to be x. So that means dx dt is going to be 10 meters per second. And there's my angle theta. We are looking for the rate change of the angle. So that's my, that's my unknown. Okay. And we are told that the distance from the camera to where the balloon started was 200 meters, and we want to find this at the instant the balloon is 150 meters high, so the instant that x is 150. So I need to figure out what y is, and I can do that using Pythagoras' theorem. Okay, so y squared is going to be 200 squared plus 150 squared. So that's y squared is going to equal 62,500. And if I square root that, I get y is actually plus or minus 250, but we can only deal with the positive because it's a distance. So y is going to be 250 meters. Okay, so I've got my three sides of my triangle. Okay, so now I am going to set up a trig ratio. Okay, and to do that, I am going to set up a ratio between the side x, which is changing, and my base, which is 200. So therefore, I can say that the tan of theta is going to be side x over 200. And now, if I take the derivative of both sides with respect to t, the derivative of tangent is secant squared theta times d theta dt is going to be equal to the derivative of x over 200 is just 1 over 200 times dx dt. And now I have to come up with a value for secant theta, okay, because I know what I know this value is provided. I want to come up with a value for secant theta divided over, and I'll get d theta dt. So if I look at my diagram, secant theta is equal to the hypotenuse over the adjacent, so it's going to be 250 over 200, which reduces to 5 over 4. So therefore, in this equation, secant theta is 5 over 4 squared times d theta dt is going to equal 1 over 200 times 10, which was dx dt. And if I simplify this is going to be 25 over 16 times d theta dt is going to equal to 10 times 1 over 200 is going to be 1 over 20. And then to get rid of the 25 over 16, I will multiply both sides by 16 over 25. And therefore, d theta dt, if I work this out, is going to be, if I reduce my fraction, 4 over 125. It's going to be radians per second. It's going to be the change in my angle. So that is how you do a trigonometric problem. So again, good reference in case you do see something like that. I have seen one question like this on an AP multiple choice exam, okay, but I haven't seen one on a free response. So I don't know if it's a big focus of the course, but kind of good to be familiar with it anyhow. Okay, there's your assignment on shadow problems and on some trigonometric problems, or the Pythagorean problems, sorry. So give those a try, and if you have any questions, you can ask me in class.